Hey guys, in this video I'll be doing like a simple gradient descent with one feature and one bias term, but you can do this for as many features as you want, tens or hundreds, but for simplicity I will do it just for one. And just for formality I will show you the equations we are solving. So we will be solving this equation where theta is our parameter. You can think of it as uh, your parameter that you multiply your x's by to get the y's. Um, and so we will have theta I, which will be our previous theta, minus the learning rate alpha, and then this will be multiplied by the difference between the hypothesis, which is just a fancy term for the y's that we get from the model, minus y, which we have given the model, and this will be multiplied by xi, which will be our input features. And we will do this repeatedly until we get the hypothesis close to the y. Um, so the hypothesis can also be written as theta I times by xi, where theta will be our parameter, like I said. So if you look at the equation y equals mx plus c, this will be m, and xi or x1 will be our x, input x, and then for c we can just assume we have c is also a parameter. We will call this parameter 0, and x0 will be x0. So you can say x0 to 1, or you don't even need it because we are just using one feature anyway. So now I will import some basic libraries that will be helpful for this. So import numpy as np. This is good for multiplications, or making an array of numbers, or making ones and zeros. From matplotlib, no, import math. This is good because we can use functions like pi or exponent, and we don't have to just copy paste the number. Import matplotlib.pyplow as plt. So we will compare results with this function, and finally we will import pandas as pd. Honestly, you don't really need these libraries, but I just like to use some of the features they give us. So let's get to it. So x0, like I said, you will set to 1, but honestly you don't really even need it because it's multiplied by 1 anyway. X1 we will just make a simple array, so np.array, and x, excuse me, so this will be 1, 2, 3, 4, 5, 6, 7, 9, 10. In fact, let's even have a 0. We don't need to, but let's just say. So I made my x's. Now we will make y. So y, we will simply multiply these numbers by e, the Euler number e, which is 2.718, I believe, and we will add some noise to it. So we will just do x1 multiply by math.e, and then we will add some noise to it. So let's just say 2. So if you look at our equation, y equal mx plus c, c is basically the bias, which is 2, mx is this, m will be the e value of e, which is 2.71, and x1 is just these numbers. So I will get rid of this. I will show you x1, and I will show you y. So when y is 0, we sub in 0 here, we just get we have this term too. When y is when x is 10, we have this term here. So it's just like 27 plus 2. So yeah, we don't really need this, so let's get rid of that. Now let's get into the actual coding, so the function. So we will have iterations. This will be how many times we run the model, and we want to reduce this error. So if we do it once, it might not be really close, but it'll still be get close, and then we do it again and again. But we need to know how many times till it gets really close or it converges. So let's say, so the difference is like this, where it doesn't get any more closer. This is our graph, so it doesn't get any more closer. So we can sort of stop the iterations here rather than here to save computational time, because it makes no difference to the outputs if we have stop here or here. So yeah, we will have this variable, and we for now we will set it to 100. We will have theta 0, which I told you is some initial guess. We will set it to 0, and theta 1, which again we will set to 0. This is initial guess, it can be any number, but just for sanity we will set it to 0, so because it's a good point and then it sort of adds up. Now there is also another thing called the cost function, but I will talk about that some other time. But now let's get into the equation. So we will have for I in range iteration. So from so it'll start with 1 and get to 100. So as that's happening, what do we want to do? Well, we want theta 1, which let me do theta 0 first, which is our bias basically. We want to, what do we want to do with our bias? Well, we want to subtract 0. We want to subtract the learning rate, which I haven't set. Learn rate, I will call it. We will initiate it here, so learn rate, and run this. I don't know, learn rate equals 0.1. 0.01. 0.01 is a good start. By the way, I press shift and enter to run a cell. So when I move to the other cell, I'll run this. Now, as you can see, it's the last thing I ran was this, because it's 6 now. So you run this, and then it will be updated in here. If you don't run this, then this won't work because we haven't updated this value. So we will have the learn rate multiplied by the sum of the sum of what? The sum of x0 multiplied by theta 0. Theta 0 is our this term, so it's the C term, intercept term, or the bias. And in this equation we can see it's true. That's our bias. So so we want to sum that, and then we want to add it to x1 times by theta 1. So basically, if you look at this equation, in fact I should have probably done that. So for simplicity, so for our example, xi, this will be theta 0 x0 plus theta 1 x1. So then we sub this into this equation for x and subtract y, and then multiply by xi. So um, we have done that. Now we simply subtract y. um, so we've subtracted y, and now we have, as you can see, it's multiplied by xi. Now xi for theta is 0. So it's just 1 basically, not 0. So when you multiply by 1, nothing really happens. But I'll just do it anyway. X0. Now we have multiplied this um, and since this is sum over all the model, we will do divide by len of x1. So this is the length, how many features there are. So there's 10 here. In fact, I'll show you. So if I do len x1, well, they're 11 because we counted 0 as well. So this will be the sum over all the models. So yeah, it's for the whole model, so we divide. Now I will do the same for theta1, which will be theta1 minus learn rate times by sum instead of x0. Well, we'll have this as well. x0 theta0 plus x1 times theta 1 minus y. Now the only difference here is we are multiplying by x1 rather than x0. The rest is all the same. Yeah, then x1. By the way, if you were to have other features, you would have theta 2 and then you'd have the same thing, but you would multiply it instead of by x1, you'd multiply it by the x2, or if this was 200, it'd be x200. But for simplicity, let's leave it at that. So yeah, I think that should be that. And wait, let's print just for sanity theta 0, theta 1, and just write bias is, and then theta 1 is okay. Now let's run this. Oh, did I forget a comma? Yeah. So yeah, as you can see, it ran the equation, and it's sort of saying my value theta 0 is 2.8, and then bias is 0.813. As you can see, it's getting closer and closer. So it starts off well up, and then it gets closer. Now I just wanted to show you that, but I will get rid of this so we don't see it for everything, but we just see it once. So we go outside the for loop and just say print. In fact, I will print it outside the for loop, so it will just print the latest one. So if I run it, that's our latest one. Now let's increase the 100 to 1000 for more for better accuracy. So you can see it's saying our theta is this, our bias is this, and our theta is 2.713. If we look at E, our value of theta is 2.718, so it's not that far off, but we can still do better. So let's just say 5,000. Yeah, why not? Let's do 5,000. Yeah, it's 2.718. Now it's much closer. Again, you can play with the learning rate, make it bigger or higher for more accuracy. But now let's do another thing. So let's do plt.plot, plt.plot. We will plot y. So this is our y that we fed into the computer, and then we will also plot what will it be. So the equation is equation equals y equal mx plus c, right? So I'll get rid of the equation. So m equals, this will be our theta 1. So m equals theta 1, c equals theta 0, and then m times by x1. X is, in fact, I will just keep it like this, x equal x1. Okay, so now if I plot the equation, you can see it's literally on top of it. It's really close. So I don't know why I imported panda. Okay, I know why I imported pandas. I'll show you. So we can look at the values digitally. So equation, if I make a data frame, let's say table equals pd.data frame, data, ignore my typing. Yeah, and we will add, this will be our y given. So this is our given y table, output y. This is when we did the training, equals equation. Alright, now if I print the table, you can see. So y given was 2, y trained was that, and you can see that it's really close. And yeah, that's basically a simple version of gradient descent, and I will end my video with that. And if you want more in-depth analysis, you want more features, so I've just done x1 and bias. I can make another video, let me know. And yeah, that's how you do gradient descent. And in fact, you don't even need these libraries apart from maybe E, but you can simply Google the value of E. But yeah, that's how you do it. Thanks for watching, and let me know if you have any more requests.